Yes, so I suppose the screen is visible, right? Yeah. So let me just, yeah. So let me just start then. Let's start with a few of the questions that I had given last time. And in general, see, when I give you questions, just maybe note it down right away. I suppose most of you do that because I may not be able to upload the video or so on, and sometimes and it's better like shouldn't be looking throughout the video to search for the because the questions will be scattered throughout the videos usually throughout the class. Just note it down. That's handy. But yeah, anyways, let's start. Let's start with one question which I had asked, right? And maybe through that we can, yeah. And so the plan for today is it will just be problem solving. Okay, there will be no theory. So today will be, maybe I should just say, technique oriented. So I will not be saying any, like maybe not many insightful kind of, no, not too many words. We just look at different techniques and try to do more and more different varieties of questions up to an elementary level. Okay, because today I plan to wrap this topic up of bounding, adding up infinite things and seeing if it's finite or not. Okay, so today we'll just look at, mostly we're looking at techniques and tactics mostly. Okay. Yes. So I believe this is the first question. If I miss some question, then you can just tell me. But I think one second. Yeah, this was the first question, right? We were trying to add these. So we had this number, and then we added a half in that, and then we add a 1/3, then another one, and so on. So let me just write this general term. Meaning the general term would look like till n. The question was that if I keep doing this, then what will happen to this quantity? Yeah. So the question is, what happens to the summation? Okay, one second, someone is joining. Yeah. What happens to the summation? Yeah. So if someone has tried it, please let us tell us, then we can build on that maybe. Yes, can you be a little louder? Yes, right. So this was the question we had done. I had given. I sort of think the last time that if you're adding these numbers, right, one and the one, then you add a half to it, then you add a 1/3 to it, then 1/4 to it, and you keep doing this, then what happens to the summation? What can you say? What all can we say about this? So this was a question which I think I had asked the last time. Does it? So see, there are several possibilities, right? See, certainly one thing is true that if you keep adding new numbers, obviously it's increasing, right? Even in this geometric series, it's called the geometric series. We'll look at this series more closely today. You're keeping adding, so obviously number is increasing, but we saw that this remains less than 2. No matter how much you add, it remains less than 2, right? We saw this. What happens in our question, in the current question? Anyone has tried? Because if you just try even computationally, or if you use the comparison method or grouping method that we did, what happens? So does it? There are two possibilities, right? Does it remain? I'll just write in short. Remains less than some number. And by the way, this is, yeah. Okay, so right, but okay. What is the conclusion? I'm not asking if it's very good if you have a proof also, but what is your conclusion? Does it remain less than some number? Meaning, in other words, it has an upper bound, or does it just become bigger and bigger than any number? Can you do you have you figured out what is the conclusion method? Then you can tell me after I see if the conclusion first is correct. Um, yeah. Yeah, so greedy method might have worked, and not that you should have tried over the week. But then, what was the conclusion? Because that is the first thing we want to get at. Okay. Well, all right. So if you would have tried this, tried calculating this, right? I mean, just put it in some online calculator or just do it yourself. I mean, you should do it yourself, but let's say you want to do for 100 terms also, you can just put it in some online calculator and see. You would see, and this is what I would recommend, because maybe we don't yet are not that mature improving, but yeah, you will see that this is unbounded. Yeah, so this is not the case. Becomes unbounded. Becomes unbounded. What does this mean? This means that as you keep adding more and more numbers, this thing grows, and it grows bigger than any number. Did anybody reach to this conclusion? No. Okay. Let's say that this is the conclusion. Okay. So that it. Okay. Okay. So I had even said it. Okay. So then the question was this only. Okay. Right. Okay. So how do you show it? Do you have any, has anybody done calculations and seen that, yeah, I added up to 1,000 terms by calculator and saw that it was more than this, then I added to 1 million and saw that it was bigger than this? Because that's not a proof, but that's also a pretty good, just to work, and you get an estimate as to how fast it's growing. Anyone done something like that? Okay. So anyways, we will obviously not do that. I'll not do that here, but we will show how it becomes unbounded. Okay. Let me just try to expand this a little bit. What does it mean? Maybe, I mean, you understand in the English words what it means, but I mean, what does it look like in numbers? It means something like this. Given a number, say 1,000. Okay, let's say I give you a number 1,000. You will have to produce me a big N such that if you add it till there, now I don't know what that N is. I mean, I have a rough idea. It's 10 to the power 1,000, something like that. Maybe that's too big, but something like this. You have to give me a big N such that if you add this many terms, it will become bigger than 1,000. So is it clear? This is the kind of thing this means, that now if I give you 10,000, you can again give me a bigger number, or maybe you cannot give me explicitly, but you can convince me. You can give an argument as to say that yes, it will become bigger. Okay, that is what we are trying to do. Okay, but surprisingly, so I'll erase this point. Okay, this is just expanding. Surprisingly, the technique remains very similar to the grouping and comparing that we were doing the last time. Okay, let me not review that. Let's just do this here and we will see that same kind of thing. That is really the beauty of this. So it becomes unbounded, and we are the technique would be grouping and comparing. So as you can understand, it's a very powerful technique. Let's try to see this. So this becomes unbounded, and the technique would be grouping and comparing. So let me maybe mention that. Comparing. Basically, these two words are in some quite powerful. I mean, just if you get the gist of this technique, then you don't have to remember most things. You don't have to remember at all. You just be able to do it organically. But in any case, let's do it now. Okay. Before I do this though, let me mention one more thing. Okay, this series is unbounded, meaning it does become bigger than anything you can, any number. It but the thing is that it grows very slowly. I will give you an exercise on this later on. I'll just have to do the proof, but it grows very slowly. What does it mean? It means that even for this number to become 10, even for this thing to become 10, you will need a lot of terms. After a long time, it will become 10. Okay. So before I do this, I'm giving one exercise which over the weekend you can just try exploring it in all ways you can, and just try this. So give an estimate, or let me just write it in more term. How many terms, and later on we'll see there are proper ways to do this, but currently I don't think we have the tools, so I don't want to say it currently. Okay, but just try it first and see where you can go. Maybe there's an alternative. How many terms are needed? So when I say how many, I don't want a precise answer. A rough answer will do. Cannot, obviously. Yeah, in any case, yeah. How many terms are needed for the sum? Soon we'll put a good notation there, but for now, let's say for the sum to become bigger than 10. And if you can do this very easily, if this is very easy for you, then just make it 100 and try. So give a ref. Don't like, if you can just say, I mean, you can just say I'll just try for this. You can say something like that, but this is not a good bound. This is just an impossible thing. This will obviously work, but you want a reasonable bound. How many terms reasonably you want to calculate so that it becomes, so that you can guarantee it to be more than 10. 10 terms will not be enough. If you add till 1 by 10, you're not going to get 10 surely, right? And that's why the series is a little misleading. This series can make you think like, this will be finite. I think someone had tried earlier for a few terms and they saw that they